Theorem 9. If G is continuous at A and F is continuous at G of A, then the composite function F compose G given by F compose G of X equal to F of G of X is continuous at A. The proof is we know that the function G is continuous at A, so by definition of continuous, we have the limit of G of X as X approach to A equal to the G of A. We also know that the function F is continuous at G of X, so we have F of G of X, the limit as X approach to A equal to F of, we use theorem number 8 to pull out the F outside, and is equal to F of limit of G of X as X approach to A, and this is mean G of A. So we get F of G of A. So by definition of continuous, we can conclude that F compose G is a continuous function. We have example number 9. To do example number 9, we need to identify the composite function. So in general, the most outside one is psi of x. So your f of x will be psi of x, and your g of x is x squared. So now we check again. If we do f compose g of x, we will have the function is psi of x squared. Okay, so it means we can say that the function h of x is the function composed of f compose g. Okay, so then we need to identify the domain of each function. The domain of the function f is all real number. The domain of function g is all real number. So g is all real number. So G is continuous at everywhere. F is continuous everywhere and is continuous at G. For G at any number, then the function H is continuous at all real number, at everywhere. So H of X is continuous on R. In part B, the most outside one is the function f of x is ln x. And the function g is 1 plus cosine x. 1 plus cosine x is continuous everywhere. It means continuous on R. But the ln of x has to continuous when x is positive. It means that when you plug the function g into the function f, the 1 plus cosine of x have to be positive. But recall that the cosine of x is between negative 1 and 1. So between negative 1 and 1, if you plug any number that other than negative 1, more than negative 1, this expression is always true. But if you plug in negative 1 for the cosine of x, 1 plus negative 1 will equal to 0. Then the function f of x is not defined. So this is true only when cosine of x is not equal to negative 1. Or in the other word, we can say like this. We can say the function h of x is not continuous at cosine of x equal to negative 1. Now we can solve for this, right? So if we draw the circle And we look at this point right here, pi. So we got -1 comma 0. So this point right here is pi, or 3 pi, or 5 pi, or 7 pi, and so on. Or this can be minus, right? Plus minus. Okay. So if you notice that 1, +1, -1, +3, -3, +5, -5, +7, -7, and so on, they are the odd integer. So instead of list them all down a lot like this, we can say that h of x is not continuous at x equal. So we use 2n to represent for the even, for any number n. And then to represent for the odd, we just go ahead and add 1. Or you can do -1, okay? And then this is represent for the odd number, like 1, 3, 5, 7. Or you plug in any number negative. For example, let's do -20. Then you will get -40 plus 1 is -39. It means this right here, okay? Pi. So h of x is continuous everywhere except at x equal to 2n plus 1 pi. For n is in the integer. The notation for the integer is z.